Okay, thank you for coming. I'm sure for most of you the feeling is not mutual, but it's great to see you today. We are going to get into the second part of the final exam review. So if you were here in class on Wednesday, we went through the first 6 problems, and then we're going to go up to number 24 today is the plan, and then finish the last 10 in the last day on Monday. So again, broken up into 3 parts for reasons beyond my control, but that's how we're going to do it this year. All right, so where we left off last time, we were in the middle of some questions dealing with sort of quantum theory, so that there's a lot of topics that sort of fall under that umbrella with quantum numbers, electron configurations, and so on. And one of the other major topics, which we will see in this first question here, is about the Bohr model of the hydrogen atom, and specifically wavelengths of or frequencies of photons that are either absorbed or emitted when an electron undergoes a transition in one of these atoms. So as usual in this review session, please stop me with any questions you have either on the specific question we're doing or anything closely related to the topic at hand, so we can make sure we cover everything that you guys are interested in learning today. All right, so this number 7 here starts with the description of a hydrogen atom which undergoes a transition from n equals 4 to n equals 2. We want to know what is the wavelength of photon that is absorbed or emitted during this transition. So the first thing to think about, which can help us eliminate some of the answer choices, is whether or not a photon will be absorbed or emitted during this process. So we're going again from n equals 4 to n equals 2. So these different n values represent the relative energy levels from lowest to highest. And they get closer and closer together as we go up, as I try to show here. So we have these different energy levels. They go up to infinity, obviously. And here we're going from n equals 4 to n equals 2. So as we go from n equals 4 to n equals 2, as you can see on this diagram, we're going from a higher energy to a lower energy state. And so the electron is losing energy. And it loses that energy in the form of a photon and emits that photon. So whenever we have a transition from a higher value of n to a lower value of n, that's going to result in a photon being emitted. And then if we go in the opposite direction from lower n to higher value of n, we're going to absorb a photon. So those are the 2 different processes that can result in an electron changing its energy levels. It'll stay at the same energy level until one of those 2 things happens. Either absorbs a photon and goes to a higher energy level, or as it comes down to a lower energy state, it's going to emit a photon. And those are the 2 possibilities we have to consider here. So we know that a photon is going to be emitted, so we can automatically eliminate choices A and C, because no matter what the wavelength is, it's not going to be absorbing in this case because we're going from higher n to lower n. And then from there, the next step is to do this numerically. So we're going to use the Bohr equation. So anytime we're talking about transitions in a hydrogen atom, we want to think about this Bohr equation, which the most useful form, and the one that we most often use, is in terms of delta E, which is the difference in energy between 2 levels. So it has this constant out front, minus 2.18 times 10 to the minus 18 joules, which is just the negative of hydrogen's ionization energy. And then we're going to do this in terms of n values. So we go 1 over the final n value squared minus 1 over the initial. All right, so again, this is talking about a difference in energy, so it depends on the 2 different n values that we were starting and ending at. So for this particular example here, we're going to put that constant out front, and the 2 values of n are going to be 4 and 2. So the final value is where we're ending up, which is n equals 2, and the initial value is n equals 4. So we're going to put those 2 numbers in like that, and we get a delta E of negative 4.088 times 10 to the minus 19 joules. For this particular problem, it's not critically important that we get the sign of delta E correctly, because this negative, again, just tells us that we're going from higher to lower value. What we're going to end up calculating in the next step is going to be the wavelength of the photon. Wavelength is always a positive number, so basically the energy of the photon is going to be just equal to the absolute value of the change in energy. So if we have a negative delta E, that tells us that a photon is emitted. The energy of that photon is just that absolute value. You can never have a negative photon energy. But delta E itself, which is the difference between 2 levels, could be positive or negative. All right, so we're going to use this equation. The energy of the photon is just the absolute value of the difference in energy, and that's going to be equal to hc over lambda, which is one of those photon equations that we reviewed last time in the first part of the review. So typically these Bohr transition problems involve 2 steps. There's the Bohr equation, and then there's going to be one of our photon equations, which I'm missing my pointer again, so let me get that back. All right, so now you guys can see what I'm pointing at. So basically the first step is always going to be the Bohr equation typically. And then once we have that delta E, very often we're going to translate that into either a wavelength or frequency of the photon that's involved in that process. So that's what we're doing here. We're going to solve for lambda, which is going to be equal to hc divided by the photon energy. And so h is that same constant that we saw last time a few times. Both of these constants are on your periodic table, so you're okay looking those up if you don't remember them. 3 times 10 to the 8th meters per second for C, and then we're going to divide that by the absolute value of this number, which is just taking off the minus sign, 4.088. So if the energy of the photon is 4.088 times 10 to the minus 19 joules, the wavelength that we get is 4.86 times 10 to the minus 7 meters. So the initial number we calculate from this would always be in the SI unit, which is meters. Answers are typically given in nanometers, so we're going to multiply this times 10 to the 9th to get 486 nanometers. Okay, so that's going to be choice B, 486 nanometers, which is emitted in this case. Okay, any questions on this? All right, we'll continue on. We can come back if we need to. All right, the next couple of questions deal with periodic trends. So we're talking about basically 4 major trends from the periodic table, which we can identify now. We have the first one, which is covered here, is atomic or ionic radius. We also have ionization energy, electron affinity, and electronegativity, all based on, again, trends on the periodic table. So what we're going to do for these is select the largest atom or ion from the following list. So in this case, we're comparing atoms and ions to each other, so we often have to think about a couple of different factors here. If we were comparing just neutral elements, so atoms that don't have any charge, we could use the periodic table, and as a reminder, if you're just comparing the radii of just neutral atoms, it just goes by, it's going to increase as we go top to bottom. So every time we go to a higher n value, we're going to add subshells, we're going to go farther and farther away from the nucleus. That's going to increase the size, but it's going to decrease as we go left to right, because as we go left to right, we're adding protons to the nucleus. We're putting electrons into the same subshell, so in that they're going to pull closer. So we have increasing radius top to bottom, decreasing radius left to right. That would be the trend we would want to follow if we're going to be talking about just neutral atoms that don't have any charge associated with them. And there's really no exceptions to that trend that we need to worry about. But in this case, we'd have a bunch of ions involved. So whenever you're given ions and asked to think about their atomic radius, you can't just look at their location on the periodic table. You have to first think about how many electrons do they have, what is their electron configuration. And so if we look at these answer choices, we have calcium 2 plus, K plus, argon, and Cl minus. So calcium 2 plus, we remove 2 electrons from calcium, that's going to have 18 electrons, the same configuration as argon. K plus, we remove 1 electron, has 18 electrons, same as argon. Argon has that number of electrons, and then Cl minus also has 18 electrons. We add 1 to Cl to get to Cl minus, which has also 18. So all 4 of these first choices have the same electron configuration, which is that of argon, 18 electrons. And then if we go to choice E here, which is Br minus is the same column as chlorine, but it's 1 row down, and that's going to have the same configuration as krypton. It'll have 36 electrons. Okay? So we're looking for the largest atom or ion from the list, so we want the largest one here. If we compare choices A through D, these are all what are called isoelectronic, so that means they have the same number of electrons. And whenever we're comparing isoelectronic atoms and ions, basically the easier way to remember it is that the more negative charge you have, the larger it's going to be. The real reason for this is that the more negative charge means they have less protons in the nucleus, so they're not going to be able to pull the electrons as close. The more positive charge they have, means they have more protons in the nucleus. So basically, if we have these 4 choices here, calcium has 20 protons, potassium has 19 protons, argon has 18, and Cl minus has 17 protons. Those are their atomic numbers. And the one that has the most protons is going to be the smallest, is going to pull the electrons in closest to the nucleus. The one that has the fewest number of protons is going to be the largest. So we rank them from most positive to most negative, and that means for this first set of 4, We have calcium 2 plus is going to be the smallest. It has the most protons in the nucleus, or the most positive charge, however you choose to think about that. K plus is next, argon, which is the neutral, and then the largest of these four is going to be Cl minus, which has the most negative charge or the fewest number of protons. So with isoelectronic ions, which is a situation you may encounter on the exam where you have a bunch of ions and atoms that have the same number of electrons, you need to think about how many protons they have in the nucleus, not their location in the periodic table. But then for these last two, we have to compare. So Cl minus is the largest of those four, but we're looking for the largest overall. So we have to compare Cl minus to Br minus. These two are not isoelectronic. And in this case, they're going to be related to each other by their position on the periodic table. So Cl minus has the argon configuration, Br minus has the krypton configuration. As we said, as you go down a column of the periodic table, you get larger and larger because the electrons are put into higher numbered subshells that are further and farther away. So in Cl minus, the valence electrons are in a 3p subshell. In Br minus, they're in a 4p subshell. Those should be farther away, and so Br minus should be larger than Cl minus. So when we're comparing these two, we get that Br minus is larger because of its location on the periodic table. The radius increases as we go down a group. And the number of protons is not the important factor in this case because these don't have the same number of electrons. So only if they have the same number of electrons do we really hone in on the number of protons as being the more important factor. All right, so that's going to be the winner then is Br minus. It's going to be the largest of all five of these. All right, any questions on this one or on atomic ionic radii in general? Okay. All right, and then number 9 deals with another periodic trend. So we're looking for which one has the smallest first ionization energy. And again, what we're looking for here is primarily the location on the periodic table. So for first ionization energy, that's the removal of the first electron, which is that valence electron is going to come out first from the atom. And the location of the periodic table is also very relevant here. So if we have the periodic trend that we covered in class last time before starting the review problems was that ionization energy typically increases as we go bottom to top, and it increases as we go left to right. Although there are some exceptions in this that we need to be aware of potentially for these problems. As usual, when we're doing problems like this that have 5 answer choices and we're just trying to either rank them or pick the largest or the smallest, I think it's helpful to just compare 2 at a time, and in particular to compare 2 that are fairly obvious based on their location on the periodic table. So if we look at the first 2, which is sodium and boron, we're looking for the smallest ionization energy. So for sodium versus boron, we go to the periodic table, we see that sodium is here in group 1, and then boron is up here. So boron is both to the right of sodium and 1 row higher, so both of those would expect it to be larger on account of both of those trends, across and up. So boron is definitely a larger ionization energy than sodium. And we're looking for the smallest one, I suppose, so we need to take that into account. So boron is larger than sodium, so this is our smallest one so far, so we can eliminate boron if we're looking for the smallest. Then we're going to compare sodium and aluminum. So sodium and aluminum are on the same row of the periodic table. Aluminum is to the right of sodium. There are, as we said, some blips in the trend, but those occur at group 2. So if we go from sodium to magnesium to aluminum, we expect sodium to increase as we go from, we expect ionization energy to increase as we go from sodium to magnesium. This one should be abnormally large because it's group 2. We would have a decrease from magnesium to aluminum, but we would still expect sodium to be smaller than aluminum. So as we go across, we would expect this one to be larger than aluminum, but aluminum still will be larger than sodium. So remember we said that the trend has some breaks in it, but you never have where it skips 2 groups, basically. So if we compare sodium to aluminum, we expect aluminum to be larger. It's to the right on the periodic table. And it's not one of the places where we expect the decrease to occur. So that's going to be, again, we're looking for the smallest one, so still sodium, we can get rid of aluminum. Sodium and magnesium is a fairly simple comparison because they're right next to each other. So again, as you go left to right, you increase. We have an especially steep increase for magnesium. So magnesium increases a lot compared to sodium because it's group 2. So that one is a fairly obvious one. So still sodium, we can get rid of magnesium. And then finally, sodium versus potassium. These two are fairly easy to compare as well because they're in the same column of the periodic table. And as we go down a column from the top to the bottom, the ionization energy decreases as we go down. So potassium is going to be lower than sodium. So we finally have one that's smaller than sodium, and that's going to be the one that we pick as the lowest overall. All right, so I like to do these problems by comparing two at a time. And again, we would have to remember some of the blips in the trend potentially, but it didn't really come into play here. So for these answer choices, we should remember that as we go across this row, we'd have magnesium being larger than aluminum. So if we were comparing those two, we would rule that aluminum is smaller, even though it's to the right. That's one of the places where the trend breaks down. But if we do them two at a time, it becomes very obvious that potassium is the smallest. It's the lowest, and it's to the furthest to the left. So both of those pretty clearly identify potassium as having the smallest ionization energy of this bunch. All right, any questions on this trend? Yes. All right, so where the trend sort of breaks down, let me just, I'll go back to the periodic table for now. All right, so as we go across a row, we're going to have group 1 to group 2, we have a large increase. Group 2 to group 3, it's going to decrease again. So basically group 2 is abnormally high. And then as we go from 3 to 4, we have an increase. From 4 to 5, a huge increase. So group 5 is abnormally high. 5 to 6 is a decrease. And then it increases and increases for the rest of it. So if you're comparing two where we skip those, so if we compare, again, we said group 2 is abnormally large. If we compare group 1 and group 3, it's not that group 3 is abnormally small. It sort of fits the trend normally. It's that this one is abnormally large. So 1 to 3, you would still expect an increase. Or similar as we go from group 4 to group 6, you would still expect it to increase, this one being the one that's abnormally large of those three. So that's where the trends break down. If you look at the notes in the video from Wednesday before I started the final exam review questions, we went over that trend and showed sort of a plot that kind of gives you an idea of where those difference. And that occurs both for ionization energy and electron affinity. The difference being that at ionization energy, you have abnormally high values for those two groups, group 2 and group 5. For electron affinity, you have abnormally low values, so the trend goes in the opposite direction, but that's still where those breaks occur. All right, other questions? All right, so we are getting into some problems now that deal with, finally, chemical compounds. So everything, in the first 9 questions primarily dealt with individual elements, a little bit about compounds with mass laws, but mostly just individual atoms and their electronic structure and things of that sort. The next major part of this course deals with compounds and how they form, chemical formulas, name nomenclature, and all that stuff. So this question deals with formulas for ionic compounds. So you're going to see potentially problems like this on the exam where we give you some information in the first sentence. The formula for the oxide of gold is Au2O3. We want to know which of the following is the formula for gold hydrogen carbonate, assuming gold has the same charge as the oxide, which this we may or may not tell you. But basically the whole point of the first sentence, giving you the formula of gold oxide, is for you to figure out what is the charge of the gold cation. Because if we're dealing with transition metals or we're dealing with the metals that are in the F elements on the very bottom of the periodic table, those don't have predictable ionic charges. Group 1 elements are always +1. Group 2 elements are always +2. But for most transition metals and for all the F block elements, it's not as easily predictable. So we're going to give you the formula of one ionic compound to allow you to figure out what is the charge of that metal in that ionic compound, and then you're going to pair that metal with a different anion and figure out what's the formula of that second compound. So that's what we're going to do here. So we start with Au2O3 to figure out what's the charge on gold in this compound. And we're going to start by figuring out the charge of the anion, because the anions in these binary ionic compounds have charges that are basically invariant. So we can use the periodic table. Oxygen is in group 6, so when it forms ionic compounds, the oxygen atom will gain 2 electrons to get to a noble gas, and so we expect that in ionic compounds, oxygen will have a 2- charge, forming the oxide anion. So in this formula for Au2O3, we have 3 oxygens that each have a 2- charge. So we have 6 negative charges from the oxygen, and that means for the gold, we have 2 of them, and those have to be equal to a +6 charge overall, or 6+, I guess I'll write it the same way. And so if we have 2 gold atoms and the total charge has to be +6, what is the charge on each gold going to be? 3+. So that's going to be the charge on gold. So again, you can't look at the periodic table and easily predict that gold is going to form a +3 cation, but once we know the formula of the oxide, that's what we can figure out. So now we know that gold is going to be +3, and we're going to pair it with the other anion. So we have gold +3, and then we have hydrogen carbonate. So remember that carbonate is CO3 2-, so that means hydrogen carbonate, we put one H+ on there, and we reduce the charge to -1. So we still have to make sure we know the names and formulas and charges for all of the polyatomic ions that will come up at times on this final exam as well. So hydrogen carbonate is HCO3-, carbonate being CO3 2-, add an H+ to that to get hydrogen carbonate. So that's the cation and the anion. We just have to make sure that the two balance each other. So again, the simple way to do this is just to cross the charges and make it the subscript. So if we have the 3 goes down here, the 1 goes down there, the formula would give us 1 gold and 3 of the hydrogen carbonates to ensure that we balance the charge and have a net neutral compound. Okay? So that's going to be AuHCO3 with taken 3 times. That'll be choice C here. All right, so again, as a reminder, for many of these polyatomic ions, we have the parent ion, in this case it would be carbonate, where we have to know the formula and the charge for that. And then if we had hydrogen carbonate, all we do is just add 1 hydrogen to that and 1 positive charge. So hydrogen carbonate is still an anion because we've only added 1 H+. It's going to be HCO3-, because it's CO3 2-, add 1 H+ to make HCO3-. So a lot of the polyatomic anions have that. Anything that has more than a -1 charge, you can do that with. So we'd have, for example, sulfate is SO4 2-, hydrogen sulfate is HSO4-, or phosphate is PO4 3-, you'd have hydrogen phosphate, which is HPO4 2-, dihydrogen phosphate, H2PO4 1-, so you can always add H+ to the formula to change the charge and change the formula a little bit for a lot of these polyatomic ions. So make sure you know the names of all of them, but there's a little bit of a systematic way of doing it for many of these as we see here. All right, questions on names and formulas? Okay. All right, number 11 is our favorite, which is lattice enthalpy. So there is, going to be one question on the test that deals with lattice enthalpy. If you're lucky, it will involve you just comparing lattice enthalpies qualitatively, out of these ionic compounds, which one has the highest or lowest. We can talk about that a little bit in the future, but most of the questions that you're likely to get are going to involve lattice energy calculations, right? So we would have some ionic compound, either a real one or a hypothetical one like we have here, a whole list of information, and then we have to figure out what the lattice energy is, or lattice enthalpy as it's sometimes called. All right, so when we covered this in class, I drew the Bohr-Haber cycle, which was sort of this way of going around and rationalizing all the steps and showing that as you start and end at the same point, you end up with a total delta H of 0, and that's where this comes from. I think what's likely going to be helpful on the exam, because keep in mind that the final exam is similar in pace to the midterms, but maybe a little bit faster. I think it's 100 minutes, 34 questions, whereas the midterm exams were 4 minutes a question. This one's more like 3.5, so it's a little bit faster. And so you're not going to want to spend 20 minutes on this problem, because that's not going to help anybody, because it's still only 1 point, right? So I think what's going to be helpful is to use the equation that we can derive from the Bohr-Haber cycle. So I gave this in class as well, so I'm going to show how we can use this to find lattice enthalpy for this compound. So the general formulas for these binary ionic compounds are M with some subscript little m, that tells you how many metals are in the formula. I'll do it with X, because I think that's how I did it in class. X with a subscript of small x, which is the number of nonmetals in the formula. And so that's going to be sort of the generic formula for an ionic compound, and we have a formula for lattice energy that relates to this. So this M and X values are going to be either 1 or 2. We're looking at pretty simple ionic compounds for lattice energy calculation. So a 1-to-1 compound like NaCl, or magnesium oxide, where they're both +2 and -2, or a 1-to-2 compound like sodium oxide, Na2O, or a magnesium chloride, MgCl2. Relatively simple ionic compounds, but we do have potentially some different subscripts here in the formula to deal with as well. So when you calculate the lattice enthalpy, again, this formula comes from the Bohr-Haber cycle, so if you're comfortable with doing that cycle, you're welcome to keep doing it. It just takes a lot longer in most cases. So we're going to solve for lattice enthalpy. That's typically what we're solving for. And the first term is always going to be just the formation enthalpy of the compound itself. Okay? So it's going to be delta H of formation, unmodified. It doesn't matter what the formula of the compound is. You just use that number exactly as is given. So you sometimes have to identify which of these terms it is. So we do need to know also the definition of these terms, because the information will not always be presented in this same way, but you have to identify which one is formation enthalpy. We then are going to have two terms associated with the metal, modified by however many metal atoms are in the formula. So little m times the sublimation enthalpy of the metal, and then little m times the ionization energy for the metal. So again, both of these terms deal with the metal. And then the next two terms here deal with the nonmetal. So you're going to have the dissociation enthalpy. So typically the nonmetal in its standard state is going to exist as X2 as we have here. You can look at the given information to easily identify that that's the case. We have X2 as our standard state for our nonmetal. So we're going to take X over 2 times the dissociation enthalpy, which is the enthalpy change associated with breaking this up into individual atoms. And then we're going to have X times the electron affinity of the nonmetal X. So to help us figure out and remember what some of these terms mean, delta H of formation is typically going to be the only term we give you that involves the compound itself. So as you're looking through the list of terms that we give you, look for the one that involves the actual ionic compound. And even if it's not abbreviated as delta H of formation, the one that has this as the product or this as part of the abbreviation for the parameter, that's going to be your delta H of formation. The rest of these terms all deal with the individual elements that make up the compound. So this one is going to be identified as the one that's associated with the whole compound, so that's pretty easy to find. Sublimation enthalpy is metal solid to metal gas. So if we don't abbreviate it that way, it's going to be the term that's associated with the transformation of the metal from the solid phase to the gas phase. We learned about sublimation much more recently in Chapter 9, so that makes hopefully a little bit more sense now. And then we have the ionization energy of the metal particularly, so we don't need ionization energy for both. Ionization energy, as we recall, is removing electrons. It's the metal that loses electrons to form cations in ionic compounds. And then we have the dissociation enthalpy. This would be for the X2 standard state of the nonmetal. Because remember, when we do formation, we form the elements, or we're doing, and we get X2 as the standard state for the nonmetal. We have to dissociate that into X. Remember that this term is 1/8 times dissociation enthalpy if you have a metal sulfide. So if sulfur is the nonmetal in this case, the standard state is S8, so you can't use X/2, you use 1/8 instead. All the metal sulfide compounds would give you only have one sulfur in the formula, so you typically would just multiply that number by 1/8. Okay? So that's the one place where this formula can change, is for metal sulfides. Every other term is exactly the same no matter what. And then this last term, the electron affinity, is for the nonmetal X. So that's what we want to use to calculate lattice energy. So if we start putting in the numbers for this compound, delta H of formation is abbreviated exactly like that here. This is M2X. So that means little m equals 2, little x equals 1 for the coefficients. And so we have delta H of formation, which is minus 335. And then we have, a minus sign, minus m, which is 2, so there's two metals in the formula, times the sublimation enthalpy. Remember, sublimation is metal solid to metal gas. That's this term here, 79 kilojoules per mole, solid to gas. So we're going to take 2 times that number. Minus 2 times the ionization energy. Now what you'll notice in this problem, which we sometimes do, is we give you two ionization energies. We give you the ionization energy of the metal here, the ionization energy of the nonmetal here. Which one do we need? Only the metal. So if we give you the ionization energy of the nonmetal, ignore it. We're not losing electrons from the nonmetal, so we don't need that number. All right, but we do need this one here, the ionization energy of the metal, which is 525 kilojoules per mole. Minus x/2 times the dissociation enthalpy. Our formula in this case has one nonmetal, so the coefficient small x is 1, so we're going to multiply this term by 1/2, and that's going to be the energy for going from x2 to 2x. So this is x2 going to 2x. Is that term there, which is 178. We're going to multiply that by 1/2. And then finally, minus x times the electron affinity. There's only one x in the formula, so we just multiply that term by 1. and the electron affinity is going to be, in this case, a sum of two electron affinities, because this is technically an X2 minus anion that we're forming. But typically, in every case, we would give you these grouped together. So you're going to just take this combined number and use it exactly as we give it to you. So whether it's one electron affinity or two, you just use the number the same way, and we're always going to group them together, so you don't have to worry about separating them. All right, so we're going to just give 123 kilojoules per mole for the last step. So this numerically comes out to minus 1,755 kilojoules per mole is the lattice enthalpy for this compound. Okay, so any questions on this type of calculation or lattice energy in general? All right, it's only, as I said, it's only 1% of your grade, so don't flip out about it too much, but it is one of the more, tedious things that we did in this course, because you do have to have, there's 5 terms in this equation. 4 of them, this one, this one, this one, and the last one are the same for every compound, but you do have to remember in some cases you have to modify this term if it's not a X2 diatomic nonmetal, but if it's sulfur, which is octanuclear S8, okay? All right, anything else on this? All right. All right, the other topic we had from this part of the course was using bond energies to estimate enthalpy changes. So in our course we learned in Chapter 7 a lot of different ways to sort of calculate delta H, both using heat calorimetry or also using Hess's law, delta H formation, all those things. The first one we learned about back in Chapter 3, which at the time we didn't even really know we were calculating enthalpy change, we called it delta E at that time, was using bond energies and estimating that from that sort of data. So what we have to remember is that if we're calculating delta H from bond energies, or bond association energies as they're sometimes called, it's going to be, again, a sum of reactants and products, but this time it's going to be reactants minus products. So we have to remember, and this is always a little bit of a sticking point for some people, is that when we're using bond energies, we do the sum of the reactants minus products. If we're using delta H of formation values, it's the opposite, products minus reactants, okay? So those are two different ways of determining delta H, and because of how the different terms are defined, bond association energy is defined as the cleavage of a bond, delta H formation is defined as the formation of a compound, and it turns out that these end up flipping in those two different equations. So for bond energies, it's going to be reactants minus products, all right? So the first thing we have to do then is we have to figure out what types of bonds do we have in all of our reactant and product molecules. Because for this approach, we're not taking any sort of property of the whole compound as a whole, we're taking properties of individual bonds and summing up all of those. So we have to write out Lewis structures for all these compounds to make sure that we know, and especially for the ones that involve oxygen, because you'll notice here that we have bond energies for carbon-oxygen single bond, carbon-oxygen double bond, carbon-oxygen triple bond. So we have to know in all the compounds that contain carbon and oxygen, is it a single, double, or triple bond to be able to distinguish which bond energy we use. So in some cases it's pretty obvious which bond energies you have to use, but in cases like this, we need to make sure we draw out the Lewis structure at least mostly correct and know what the bond order is. So our first reactant is CO. So if we draw the Lewis structure for CO, that's going to be 10 valence electrons. So if we start by completing the octet for oxygen, that leaves only 2 for carbon. So this would be the preliminary Lewis structure for CO, but we notice that the carbon only has 4 valence electrons, so we're going to take 2 pairs from oxygen and turn them into triple bonds. So carbon monoxide, which helpful to remember, is a carbon-oxygen triple bond, probably the only common compound that has a carbon-oxygen triple bond at all. All right, so this one's a triple bond, so that we had to know that. 2H2, of course, is just a single bond between the 2 hydrogens. And then the product that we're forming is CH3OH. So remember, in these sort of shorthand formulas, the hydrogens are typically bonded to what comes before them often, or usually to the... So if you see CH3, that means there's a carbon with 3 hydrogens on it. And then that carbon is going to be bonded to the next oxygen, and that oxygen is going to be bonded to hydrogen. So that's the Lewis structure for CH3OH. There's also 2 lone pairs there, but those aren't important for this problem. All right, so we had to make sure we got the structures of these correct so that we know which bond energies to consider. And now we're going to do reactants minus products. So on the reactant side, our first reactant has a CO triple bond, so we have one CO triple bond to consider. And we're going to take that number from the list of bonds given, 1070 kilojoules per mole. Or just kilojoules, I guess, is fine. All right, so that's 1070 kilojoules for that reactant. And then we also have two H2 molecules. Each has one HH bond, so we're going to have a total of two hydrogen-hydrogen single bonds. So we have to multiply that number by 2, because for this approach also, we have to account for how many of each bond type we have. So if we have two molecules of H2, that means we have two HH bonds to break on the reactant side. So that's going to be 2 times that number, which is 432. So the sum on the reactant side is going to be, these two numbers added together is 1934. And then we're going to do the same thing on the product side. So we have, on the product side, our first product here is, well, it's only one product, but if we look at what's present in this, we have a bunch of different types of bonds. So we have 3 bonds between carbon and hydrogen, 1, 2, 3. So we have 3 CH bonds in the formula of our product. So we have to count those 3 times, because there's 3 bonds we have to form in that case. So we're going to take 3 times the CH bond energy, which is 413, which is 1239. We have 1 carbon-oxygen single bond, so the bond order from carbon-oxygen went from triple to single, so our product has 1 carbon-oxygen single bond now. So we don't use the double bond energy at all. We're going to use the single bond energy of 358. There's only one of those, so we just have to take it once. And then we have 1 OH bond. So this OH bond here also has to get counted. And OH bonds are 467 kilojoules per mole. All right, so the sum on the product side is going to be these 3 numbers added together, which is 2,064 kilojoules. And then finally, the sum of reactants minus products, which is what we need to do to find delta H using bond energies, is just the subtraction of those 2 numbers. 1934 kilojoules from reactants minus the 2,064 from the products gives us minus 130 kilojoules. All right, and this hopefully makes a little bit more sense now that we've had Chapter 7 under our belts, where we talked about delta H in a lot more detail. So what you'll notice is that this is an exothermic reaction. We estimated negative delta H, and the bond energies on the products are larger than the reactants. That's one feature of exothermic reactions we talked about. When you have an exothermic reaction, you have stronger bonds in the products than the reactants. We see that that's true here. The numerical sum of the product bond energies is larger than the numerical sum of the reactants. That gives us an exothermic reaction. Okay, any questions on this one? All right, this takes us back a while, but again, it's very similar to things we did more recently in Chapter 7. Just have to remember that we flip it. It's reactants minus products, and in this case, we have to consider individual bond energies for that estimation. Okay? All right, 13 deals with Lewis structures. And with Lewis structure problems, we have to recall that there's, because these are primarily multiple choice, we can't have you draw the Lewis structure and, I can't, grade it myself and evaluate it. So we're going to ask you some questions about it. And, often formal charge is part of that, as it is here. And there's really 2 ways that we will phrase the question. So you're either going to give us a Lewis structure that minimizes formal charges, or the Lewis structure that obeys the octet rule. In cases where it's possible to violate the octet rule, especially, we'll specify whether you should or should not. All right, so in this case, we have a Lewis structure of chlorite that obeys the octet rule, so we have to make sure we keep that in mind. Remember, the octet rule tells us that any atom in the structure should have no more than 8 valence electrons surrounding it, and ideally no fewer than 8 as well, except for hydrogen, of course, which has just 1 bond. But we want to find a Lewis structure where every atom in the structure has exactly 8 electrons around it. That's going to be the one that we consider then when we calculate the formal charge on the central atom. So let's go through the process for drawing a Lewis structure. So we have chlorite. The first thing we have to know is the formula. So again, reviewing polyatomic ions, chlorite is ClO2 minus. We have hypochlorite is ClO, chlorite is ClO2, chlorate is ClO3, perchlorate ClO4. So we have that whole series of oxyanions with chlorine, and it goes from 1 to 4 oxygens. The one that's chlorite is ClO2 minus. So once we know the formula, we can start counting valence electrons. So we start with each atom in the formula, and we go to the periodic table to figure out how many valence electrons they have. So we have chlorine and oxygen. Chlorine is in group 7A, which means it has 7 valence electrons. Oxygen is in group 6A, so it has 6 valence electrons. So number of valence electrons for the main group elements comes directly from the group number. 6 for oxygen, 7 for chlorine. All right, so we have 1 chlorine that contributes 7 valence electrons. We have 2 oxygens that contribute 6 valence electrons. Are we done, or do we have to account for anything else? There's a negative charge. So anytime we have charges, we have to add or subtract electrons. A negative charge adds 1 more to the total. So we expect this to have 20 valence electrons total that we're going to arrange around 3 atoms. Okay? So now we have to draw the Lewis structure of this. And so what we're going to start with is chlorine in the center. And what I like to do is start with single bonds to the outer atoms. So we have 2 chlorine oxygen single bonds. And then we're going to complete the octets of the outer oxygen atoms first. So we have 2 valence electrons from the bonds, so we're going to add 6 more to each one as 3 pairs. So that's going to complete the octet of oxygen. And that's a total of 16 now. So 2 octets, 8 around each oxygen is 16. We had 20 to start with, so we need to put 4 more. Those 4 all go on the central atom as lone pairs. All right? And then we're told in this problem to obey the octet rule. So if we look at this structure that we've drawn, what we see is that we have octet rules obeyed for oxygen. That's what we started with. And then our central atom now has 2, 4, 6, 8 electrons as well. So 2 bonds, which contribute 2 electrons each, plus the 2 lone pairs, total of 8 electrons around the central atom. So from the standpoint of the octet rule, this structure obeys the octet rule. We don't want to make any further changes to it. All right, so what we're going to do is we're going to just keep the structure exactly as it is, and we're going to calculate the formal charge. And as you recall, formal charge is going to be defined for each atom in the formula. It's going to be the number of valence electrons that element has, or that element brought to the formula, which we calculated up here, minus the number of bonds that atom has, minus the number of non-bonding electrons counted individually. All right, so that's what we want to do. And we're looking at the central atom, which is chlorine. So the formal charge is going to be the number of valence electrons that chlorine contributed, which is 7, minus the number of bonds that the central atom has, which is a total of 2. 2 single bonds is 2 total bonds, minus the number of non-bonding electrons. So there's a total of 4 non-bonding electrons in the central atom, 2 pairs. We count those individually for formal charge. And so what we end up with is a formal charge of +1. All right, so choice C is the correct answer here. All right, and because we were told to obey the octet rule, that's fine. As it turns out, we also have -1 formal charges on the oxygen atoms, if we were calculating them the same way. So if we wanted to minimize formal charge, which we're not doing here, but if we were asked to, we would have to draw 1 more double bond. All right? Because in this structure, we have a positive next to a negative, so we can eliminate those by taking off 1 lone pair from the negative charge atom and make it a double bond. So the minimal formal charges for this would look like this. And would have 2 resonance structures, so we can move the double bond to the other side as well. And that would have the minimal number of formal charges for this molecule. All right, but here we were not asked to minimize formal charges, so we're just going to stick with this structure here and calculate the formal charge directly from that. We were asked to just obey the octet rule in this structure. All right, so if there's any sort of confusion about whether or not the structure obeys the octet rule, because the central atom is in the third row of the periodic table, we could expand the octet in the central atom. That's technically allowed. So if there's any confusion about that, we will specify whether or not to obey the octet rule if it matters for that particular problem. Okay? Any questions on this? Yeah. So where oxygen comes in with a negative charge, if we do it for oxygen in this formula, oxygen contributed 6 valence electrons. So that's the first number. Each oxygen has 1 bond. So we subtract 1. Each oxygen has 1, 2, 3, 4, 5, 6 non-bonding electrons. So that comes out to -1. So a common pattern you'll see is anytime you have oxygen with a single bond and 3 lone pairs, that gives it a -1 formal charge, which is what we see in this structure. Okay? Any other questions? All right. Let's go on then. All right, next question is just name the formula. So we talked a little bit about formulas of polyatomic ions already. This one is Al2S3, so we have to figure out the best name for it. So the first thing we're figuring out when we're naming compounds is whether it's an ionic or a covalent compound. So to figure out that, we have to figure out what kind of elements are in the formula, because remember that covalent compounds involve only nonmetals, whereas ionic compounds involve combinations of metals with nonmetals. So for aluminum sulfide compound, for aluminum and sulfur, we see that aluminum is a metal. It's to the left of the imaginary staircase. It's close to the metalloids, but it is classified as a metal. And if anybody's playing with aluminum foil, that's fairly obvious that that's a metallic type of element. And then sulfur is a nonmetal. So it's a combination of a metal and a nonmetal. So aluminum is a metal, sulfur is a nonmetal. So whenever these two are combined, that means it's an ionic compound. And the key rule for ionic compounds is that when we name them, we don't use any prefixes in the names, right? So in covalent compounds, we use prefixes to distinguish how many of each atom is in the formula. So we use the mono, di, tri, tetra, penta, and so on. For ionic compounds, we don't use any prefixes because the charge of the ion will tell us what the ratio of those should be. All right, so if we have a aluminum cation, we remember the name of the cation, we just keep the same. So the metal part of the formula comes first, and we don't change the name of that at all. Aluminum. So that's your cation or the metal in the formula. And then for the nonmetal, we're going to take off the regular ending and put an IDE ending. So really for the names of both covalent and ionic compounds, for binary compounds specifically, IDE is the ending in both cases. But ionic compounds, we just put that on the second element, so we have an IDE ending on the anion part of the formula. And no prefixes. So it'll just be aluminum sulfide, which is choice E here. All right, so this first one, A, we used prefixes, same with B, so there should be no prefixes in either of these, so that makes those wrong. This one doesn't have the correct ending on the second element, should be IDE. And then this one, we don't put any sort of Roman numerals unless it's a transition metal in the formula. So not for aluminum, which is main group, or not, and definitely never for the anion. Okay? Any questions on nomenclature? All right, the other, besides covalent and ionic, the other major category that you may have to produce a name for is acid. So make sure we review the rules for those as well. All right, and then if we're keeping track of where we are in the course, we're on now past the first exam. So that basically was the last topic on the first exam, was nomenclature and ionic and covalent bonding. Now we're in chapter 4 material, which dealt with molecular structure and bonding, DBS CPR, all those topics. So this first question does deal with DBS CPR. We're looking for which of the following molecules are linear. Okay? So as you recall, when we have a formula that only has 3 atoms in it, which all of these do, you have CO2, H2O, XEF2, SO2, they all have 3 atoms in the formula. The only 2 geometries that are possible are linear and bent. And depending on how many lone pairs are in their central atom, that's going to determine whether the formula is linear or bent. So we have to draw Lewis structures for all of these and then remember which of those geometries we give. So if we have CO2, if we quickly do the Lewis structure for this, carbon is group 4, so we have 4 valence electrons from carbon, 2 oxygens from group 6, so we have a total of 16 valence electrons in CO2. And when we draw the structure for CO2, to complete the octet on the central atom, we have to draw double bonds to each of the oxygens. And I would hope by this point in the course, having gone through this long historic journey together, that we've drawn CO2 probably like 25 times now, we should know by now that it has this structure with 2 carbon-oxygen double bonds, and it's AX2, no lone pairs in the central atom, which makes it linear. All right, so any compound of an AX2 formula that doesn't have any lone pairs will be linear. We want to put the atoms 180 degrees apart to get them as far away from each other as possible. So that one's linear, so that's one of our choices. If we go to H2O, this is another one that we've drawn a million times and should be second nature by now. And we should know that it's a bent molecule. It has 2 lone pairs in the central atom, so AX2E2 is bent. All right, so that one's bent, so we can eliminate it. We have XEF2. This one's the one that's probably the the most difficult to draw of these ones. We don't typically deal with noble gas compounds, but there are some. So xenon is in group 8 of the periodic table, so it contributes 8 valence electrons, and then we have 2 fluorines that each contribute 7. So we have a total of 22 valence electrons, if I can do math today. So 22 valence electrons, and when we arrange them around the central atom, we start with bonds to fluorine. We complete the octet, and that's going to leave 3 lone pairs for the central atom. So 16 electrons have been used to complete the octets for fluorine. That means we still have 6 more for the central atom. So this is an AX2E3 structure. 2 atoms bonded to the central atom. All these will be AX2 something. And then this one has 3 lone pairs, so it's going to be E3. So if we have AX2E3, that's going to be 5 electron groups. They're going to be trigonal bipyramidal with xenon in the center. All of the lone pairs go on the triangle for any sort of trigonal bipyramidal arrangement. And that leaves the 2 fluorines at the top and bottom in a linear arrangement. All right, so AX2E3 is also linear, so that's going to be one of our choices. And then finally, we have to look at SO2. These are all group 6 elements, so we have 6 valence electrons from sulfur, 2 times 6 from oxygen, a total of 18. And when we do the Lewis structure for SO2, we complete the octets on oxygen to use 16 of our electrons. That leaves 1 lone pair for the central atom. We would need at least 1 double bond to complete the octet of the central atom, but for VSCPR, whether we have double bonds or not, it doesn't matter. We would still predict that this is an AX2E structure, and this is going to be one of our bent geometries. All right, so that one's out as well. So 1 and 3 are the only 2 that are linear of these choices, which would be answer B. So obviously there's a lot more geometries besides linear and bent, but a good number of them do fall in those categories. So to review, if you have any sort of AX2 structure, if it's just AX2, that's going to be linear. And I think we covered almost all the possibilities here actually, but AX2E is going to be bent. AX2E2 is bent. And then AX2E3 is linear. So for the 4 geometries that involve 2 atoms bonded to the central atom AX2, it goes linear, bent, bent, linear as we add increasing numbers of lone pairs to the central atom. And that's, again, there's going to be a lot more beyond this that you're going to want to know, but for a lot of problems, knowing whether something is linear or bent, as it is here, could be part of or the entire story. So if we can get good at those ones, that eliminates a lot of time and difficulty on the exam. All right, questions on VSCPR? All right. All right, so number 16 deals with molecular polarity. And I would say I don't like making promises because then if I accidentally break the promise, you guys just destroy me. But I would say that in 99% of the questions that deal with molecular polarity, your only job is going to be to decide if the molecule is polar or not to rank it in increasing. So here we're looking for the one that has the greatest dipole moment. So you might be thinking, oh no, I have to figure out how to rank these, which one is more polar, which one is less polar. But I would say 99% of the cases, as we'll see here, as long as you can tell us whether it's polar or non-polar, that's all you need to know to answer the question. Ranking the polarities is not something that's going to almost in every case come into play. So for these 5 molecules here, the first thing we have to do is figure out whether or not they're polar or not. And that's what we're going to look at for all of these. So I'm not going to go through all the details of drawing the structures, but for CCl4, which is choice A, we get a structure that looks like this, with a bunch of lone pairs in the outer atoms. But the key point for polarity is, again, the molecular geometry. And so this is an AX4 structure. And the easy shortcut is that any structure that does not have any lone pairs in the central atom will be nonpolar. Again, that's rigorously only true if you have all the same atoms on the outside. So these are all chlorines, so that works for this one. But no lone pairs in the central atom. All of these would have the types of formulas where you just have one type of outer atom. So for that, we can use that shortcut for anything. So anything that doesn't have a lone pair will be nonpolar. There are other nonpolar geometries as well, but the 5 geometries that do not involve lone pairs, which would be the same as the 5 electron group arrangements, linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral, all 5 of those geometries are nonpolar, provided you have just one type of atom bonded to the central atom. All right, if we go to the next one, which is PF5, what we get for this one is a structure that again has no lone pairs in the central atom. So if you feel like you need more practice with drawing Lewis structures, please go through these in more detail than I am. But what you should come up with for this one also is that you get no lone pairs on the central atom. All right, so there's probably some overlap with these structures, but the key point is no lone pairs on the central atom. So it's AX5, and regardless of whether you know what the name of that is, that's also going to be nonpolar because it has no lone pairs. If we go to O2, this is the easy one because anytime we have 2 of the same atoms bonded to each other, that has to be nonpolar. We talked about bond polarity also on Wednesday in the sort of previous part of the review session, talking about difference in electronegativity. And if you have 2 of the same bonded to each other, that's a nonpolar bond. In this case, the whole compound is just that one nonpolar bond, so of course it's nonpolar. All right, so O2, N2, F2, any diatomic molecule with 2 of the same is going to be nonpolar. So that one we don't even have to draw out. If we go to XEF4, this is the one that's probably the least obvious of the pair. Again, it's another one of these xenon fluoride compounds, which are not the most common, but do exist. So XEF4, what we get is a structure that has this arrangement here, where we end up with 2 lone pairs in the central atom. And this one might be not necessarily the best to memorize. I mean, you can memorize it if you want, if you have a good memory. But AX4E2, if we draw the structure out, we get 6 electron groups, so it's going to be octahedral. So we have xenon in the center, we have a square plane, and then we have one above and below. But when we have in AX4E2, the 2 lone pairs go 180 degrees apart to be as far away from each other, and we're left with a square planar geometry. So in a square planar geometry, we have 2 pairs of identical dipoles that are oriented 180 degrees apart, so a square planar will be also nonpolar. So AX4E2, it has lone pairs in the central atom, but it's still nonpolar. And then if we go to NF3, what we end up with for the last one we have 1 lone pair on the central atom. And any of the possibilities with 1 lone pair are going to be polar no matter what. All right, so if you get a single lone pair on the central atom, AX2E, AX3E, AX4E, AX5E, all those possibilities are going to be polar if you just have a single lone pair in the central atom. So this is the only one that's polar. We're looking for the one with the greatest dipole moment. So choices A through D have 0 dipole moment because they're nonpolar. So the only one that has any sort of dipole moment, which must be then the largest, is choice E, NF3. So again, in this one, as long as you can distinguish polar from nonpolar, you'll be able to get it right because there's only one answer that's even polar to begin with. So you see that for 4 of these answer choices, A, B, D, and E, they all have polar bonds, but only one of them is actually a net polar molecule because of how those bonds are arranged in the other cases. All right, questions on molecular polarity? All right, so again, molecular polarity via CPR are closely related. And the last topic that's also closely related to that is hybridization. So we talked about valence bond theory, where you have, this is basically the bond theory where you take atomic orbitals on the central atom, or each atom that's involved in the structure, and you mix the s and p orbitals together to get orbitals of new shapes that are going to be involved in forming the sigma bonds and arranging the proper geometry around the central atom. So that was sort of the next major topic in Chapter 4, which also is closely related to the sort of AXE notation that we've been going through and the molecular geometry and all that stuff. So the formula we're dealing with here is acetic acid, CH3COOH, and we want to find out both the hybridization of the 2 carbon atoms as well as how many sigma bonds are there. All right? So if we draw the structure first, remember that CH3 means we have a carbon with 3 hydrogens on it. Hydrogen will always only have single bonds, always be on the sort of periphery of the molecule, can never be bonded to 2 things. The next one is C, so that's going to be C. And then maybe not terribly obvious from the formula, but COOH, what it means is that we have an oxygen and an OH bonded to the same carbon. All right, so get familiar with that sort of shortcut nomenclature. COOH, as we have in acetic acid or other related formulas that are called carboxylic acids, which you'll learn all about in organic chemistry, they have this formula, and I guess if I'm drawing the bonds explicitly, there should be actually a bond there as I failed to draw the first time. So that's sort of the skeleton structure, and then when drawing larger structures like this, instead of necessarily going through and counting all the electrons, there are some shortcuts that I've introduced at various points. So if we have carbon, nitrogen, oxygen, hydrogen in the formulas, which are typically the cases for these organic compounds, in almost every case, your carbon atom is going to have 4 bonds and no lone pairs. So you want to make sure that that's true for each carbon to complete the octet as well as minimize formal charge. It all relates back to that aspect of Lewis structures. Nitrogens are going to also complete their octet, but they're going to do that with 3 bonds and 1 lone pair. Oxygen has 2 of each, so still a total of 8 valence electrons, but now 2 bonds and 2 lone pairs for that total of 8. And then hydrogen, as I said, 1 bond, and that's it. No lone pairs, no second bonds ever. All right, so if you're fortunate enough to get a problem on the exam that shows a structure with double bonds to hydrogen or 2 single bonds to hydrogen, you can immediately cross it out because that can't be right. Okay, so that's sort of the patterns we want to follow for these Lewis structures. So if we look at our first carbon, even with just this sort of skeleton structure drawn, we already have 4 bonds. 3 bonds to hydrogen, 1 bond to the next carbon, so we don't do anything else at this position. If we get to this carbon here, it has only 3 bonds. We can't draw another bond this way because that would put a 5th bond on the first carbon, but we also notice that this oxygen only has 1 bond and it wants to have 2, so we put a double bond there. And then we also have to add 2 lone pairs to complete the octet of that oxygen. This carbon now has 4 bonds, 1, 2, 3, 4, and this oxygen already has its 2 bonds, so it just needs the 2 lone pairs to complete that structure. So that's, again, some shortcuts we can use to draw these larger structures, which, especially for these organic molecules like this, will work in just about every case. All right, so that's the picture, and then we have to figure out hybridization. So hybridization is just determined by the number of electron groups. So if we look at the first carbon here, how many total electron groups does it have? It has 4 things attached to it. Remember, an electron group is either an atom that's bonded to it or a lone pair attached to it. So we have 4 things bonded to this. That means we need to hybridize 4 orbitals. The orbitals available for hybridization on carbon are an s orbital, specifically a 2s orbital, and 3 2p orbitals. If we're going to have 4 electron groups, we need to hybridize 4 orbitals, so we're going to use all of those, which gives us sp3. All right, so the first carbon is sp3. The second carbon atom here, if we look at the number of electron groups, how many is it? How many things is attached to the carbon atom here? 3. Remember, we don't care that it's a double bond, it's just the number of electron groups that are bonded to it. So it's 1, 2, 3. So we have 3 electron groups for this one. We still have the same orbitals available for hybridization, but we only need to use 3 of them this time, so it's going to be an s and 2 p's, which gives us sp2 hybridization for the second carbon atom. And this one unhybridized p orbital here will be involved in the bonding with oxygen, as we'll get into here in a second. So that's the first part of the question. The second part is how many sigma bonds are there. So when you form bonds in the valence bond approach, every bond is a combination of sigma and pi, sigma being sort of the head-to-head direct overlap of 2 orbitals, pi being a side-to-side overlap of unhybridized p orbitals. And if we have a single bond, those are always going to be sigma. So every bond has 1 sigma bond associated with it. So that's going to be all sigma bonds there. This double bond, anytime we have a multiple bond, is 1 sigma and the rest are pi. So this will be 1 of each, sigma and pi. If it was triple, it would be sigma and 2 pi. And then we have 2 more single bonds that are also sigma. So in this total structure, we have 1, 2, 3, 4, 5, 6 sigma bonds. 7? Yeah. Gotta go back to first grade and learn how to count again. All right, 7 sigma bonds in this structure. 1, 2, 3, 4, 5, 6, 7, all there. Okay? This is our 1 pi bond. And as I also sort of alluded to, the pi bond is formed by taking an unhybridized p orbital that's left on the carbon atom and overlapping it with another unhybridized p orbital from oxygen. So the sigma bonds all involve the hybrid orbitals. So the sp3 and sp2 orbitals make sigma bonds. The pi bonds are made using unhybridized p orbitals that are side to side with each other. All right, so questions on hybridization or valence bond theory at all? All right. And then the last major topic in chapter 4, which was again the chapter on structure and bonding, was molecular orbital theory. And this is a theory that we typically are going to use for diatomic molecules. So even if we don't tell you to explicitly to use MO theory, if it's a diatomic molecule and we're asking you about either bond order or number of unpaired electrons, you should immediately think that, and you need to draw the molecular orbital diagram, and you need to figure out what the sort of electron configuration is. So remember, the idea with molecular orbital theory, which is a little bit different than valence bond theory, is in valence bond theory, which is hybridization, what we just dealt with in the last problem. In valence bond theory, you're dealing with individual orbitals on each atom. So you hybridize the orbitals on one atom, but they still are localized on the atom, and they overlap with the orbitals on the next atom to make the bonds. But then when we're talking about molecular orbital theory, which is the more advanced bonding theory, it's not that we have localized orbitals anymore. We actually form new orbitals that are delocalized over the entire molecule. So they're both sort of mathematical models of bonding that involve mixing of orbitals. But the difference with molecular orbital theory is that we form new orbitals that are delocalized over the entire molecule. We no longer have atomic orbitals or hybrid orbitals on each atom. We have molecular orbitals that are delocalized over the entire structure. So here we're doing it for C2, 2 minus anion. And so this is going to involve both s and p orbitals, because carbon is in the p block of the periodic table, so we have to draw molecular orbitals involving both the s and p orbitals. And we remember that we have two possibilities for the orbital diagram. So if we have boron, carbon, and nitrogen, this is P1, P2, P3, the first three elements in the P block. Or if we have oxygen, fluorine, and neon, which are P4, P5, and P6, that's the second half of the P block, we have two slightly different diagrams. So the s orbitals always mix the same way. They're going to form a sigma 2s and a sigma star. So those are always your first two orbital levels, sigma and sigma star. That's going to be the same over here. And then once we get to the higher energy orbitals that involve the p orbitals, remember that when we have p orbitals, they can mix in two ways. They can combine head-to-head to make orbitals that are sigma in symmetry, that are cylindrically symmetric, and sort of involve that head-to-head overlap, or they can overlap side-to-side and make pi orbitals. So we have three 2p orbitals from each element, from each atom, so they're going to make 6 total molecular orbitals. So you're going to have pi and sigma. In boron and carbon and nitrogen, the first orbital level is a pi bonding orbital. That's the in-phase overlap side-to-side. Then you have the sigma bonding orbital, which is in-phase overlap head-to-head. And then at the top you have pi star, sigma star. All right, so you always get, for each combination, you get bonding and anti-bonding. So we have sigma 2s, sigma star 2s. We get pi 2p, pi star, sigma 2p, sigma star. So always those bonding and anti-bonding combinations. The only difference is that when we go to oxygen, fluorine, and neon, the second half of the p block, in the 2p orbital mixing, you have sigma coming first at the bonding levels and then pi. So the first two and the last two are still the same, but these middle orbitals flip in the second half of the p block. All right, so again, it's these levels here that vary between the different types of elements. So for certain types of problems, especially if we're asking you about number of unpaired electrons, this time we're doing bond order, so it actually wouldn't make a difference. But for number of unpaired electrons, if we ask you about that, you would need to make sure that you do this correctly. So because we're dealing with carbon, we're going to use this diagram here, and we're going to put the correct number of electrons in. So the number of electrons in this is going to be number of valence electrons specifically. We have 2 carbons that each contribute 4 valence electrons because carbon is a group 4 element, S2P2. Plus we have a 2 minus charge, so we're going to have another 2 electrons for a total of 10 valence electrons. All right, so this structure has 10 valence electrons, so we're going to arrange them in this diagram from lowest energy to highest energy orbitals, okay? So we have 10 to put in here. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll notice when I filled the pi orbitals, I followed Hund's rule. I did 1 electron at a time, and then I paired them up, so that's still true for molecular orbital diagrams as well. And this is going to be the diagram that we get for C2, 2 minus. And then if we want to calculate the bond order, it's going to be 1/2, we take the number of electrons that are in bonding orbitals. So out of these 10 total electrons that we had, how many of them are bonding? Those are the ones that don't have stars next to them. So we have 2, 4, 6, 8 of our 10 electrons are in bonding orbitals. That's the most you can have. And then 2 of them, these 2 from the sigma star 2s, are antibonding. So a bond order is going to be number of bonding minus number of antibonding times 1/2. And this gives us a triple bond, which is the highest bond order you can have for a diatomic molecule. Number of unpaired electrons for this would be 0, but we're not asking that here. We're just asking for bond order. All right. So the 2 major things we'll ask you about molecular orbital diagrams are bond order, number of unpaired electrons. For number of unpaired electrons, there's only 3 possibilities. So it's either going to be 0, 1, or 2. If it has odd number of electrons in the formula, so if we did C2 1 minus instead of C2 2 minus, that would have 9 electrons instead of 10. Anytime you have an odd number of electrons, you're going to have 1 unpaired electron. That has to be the case. So you wouldn't even have to draw the diagram for that. If you have even numbers of electrons like we do here, you could have either 0 or 2 unpaired electrons. You have to draw out the diagram to know which one is which. Okay? Any questions on MO theory? All right. On to number 19. All right, so if you're keeping track, we're on to Chapter 5, which deals with moles and stoichiometry. And the first major topic in Chapter 5, and there will likely be an exam question on this topic, is the definition of atomic mass. So we use atomic mass all the time to calculate molar masses, and then use those involving calculating moles and things like that. So those are very useful concepts for a lot of things. But the first thing we talked about was just the definition of atomic mass. So if we have silver, remember that in most elements, this is one of the very first topics we covered, most elements are composed of 2 or more isotopes, where they differ by the number of neutrons in the nucleus. So silver has primarily 2 isotopes, 107 and 109, where again, this is the mass number that tells you the number of protons plus neutrons. So these have different numbers of neutrons in the nucleus. They have their associated masses individually as 106.905, 108.905. If the atomic mass of silver is 107.87, what is the percent abundance of 107 silver? So this number, 107.87, is the number we would get off the periodic table. And what it represents is the weighted average of the individual isotope masses. So naturally occurring silver is made up of both of these isotopes mixed together. And so the atomic mass that we report is the average of those 2 masses weighted by their abundances. So what that looks like mathematically is that the atomic mass is equal to the fractional abundance, or just the fraction of the first isotope, 107 in this case, times its mass, plus the fraction of the second isotope, 109, times its mass. All right, so for each isotope, fraction times mass, fraction times mass. What we're looking for here is the percent abundance of 107 silver, but we don't know the fraction or percent of either of them. We know the masses of each of these, so this is all given to us, but we don't know the fractions. So we're going to call those variables x and y, and then the other relationship is that x plus y equals 1. So we have 2 fractional abundances for the 2 isotopes. Those equal together 100% or 1 as a fraction. All right, so those are the 2 equations, so we can put the numbers in now. The atomic mass is 107.87. That was given in the problem, or that's the number we would get off the periodic table. And that's going to be equal to the mass of the first isotope times its fraction. So the mass of 107 silver is 106.905 multiplied by the fraction, which is x. And then the second isotope has a mass of 108.905 multiplied by its fractional abundance y. So these are the 2 equations that we have, x plus y equals 1, and then this that deals with the atomic mass of the 2. And what we're solving for here is the percent abundance of 107 silver, so we initially want to get x, which is represented in this equation there. Okay? So we can rearrange this as y equals 1 minus x, and we're going to substitute that in for y. All right, so 107.87 is equal to 106.905x plus 108.905 times 1 minus x. And when we solve for x, which shouldn't be too difficult at this point, we get x, which is equal to the fraction of 107 silver, the smaller isotope, is 0.5175. And be careful on these problems. We're typically going to ask for percent abundances, but we could ask for fraction or percent. Make sure you keep those two straight from each other. So if we were asked for the fractional abundance, we stop there. Fractional abundance is out of 1. But here we're asked for percent, which is out of 100, so we have to take the fraction and multiply it by 100, which comes out to 51.75%. All right, so naturally occurring silver is roughly equal amounts of 107 and 109. 51.75% for 107, a little bit lower than that for the 109 isotope, which would be just 100 minus that. All right, so if you see any problem that deals with atomic mass and isotope masses and how they relate to each other, this is really the only equation you'll have. And we're not going to make it any more complicated than having two isotopes, at least if we're going to solve for the abundances. But you're going to use this equation for however many isotopes you have to find the atomic mass if we ask you to do that. Okay, questions? All right, we're on to mole conversions now. So what we have here is we want to know how many phosphorus atoms are found in 5 grams of calcium phosphate. All right, so we're going to figure out, again, number of phosphorus atoms. And then we have starting with 5 grams of calcium phosphate. So the first thing we have to be able to do is find the formula of the compound, because we're going to need the molar mass to convert the grams into moles, and we're also going to need the formula at the end to figure out how many phosphorus atoms are in the formula. So we need the formula of this to be correct. So as a review, if we have calcium phosphate, we go to the periodic table to find calcium's expected ionic charge. Calcium is in group 2, so we expect it to form a 2+ cation, losing 2 valence electrons to make a noble gas configuration. So we have calcium 2+. Remember that in ionic compounds we don't have any prefixes, so we have to think about the charges of the ions to figure out what the formula will actually be. So we have calcium 2+, and then phosphate, remember, is PO4 3-. So if we take the charges and swap them, that'll give us the balanced formula, which gives us Ca3, so this 3 goes as a subscript on calcium, this 2 goes as a subscript on phosphate, so we have 2 phosphates. So this will be the correct formula for calcium phosphate, and now we're ready to go and start doing the mole conversions that we need. So we're looking for the number of phosphorus atoms in 5 grams of calcium phosphate. All right, so the first step is going to be, if we want to know the number of atoms, remember that's related to Avogadro's number, so we need to go to moles first. Avogadro's number will tell us how many atoms are in 1 mole, but we don't have moles yet, so we're going to convert that. So to do grams to moles, which we've done a million times this semester, we need the molar mass of calcium phosphate. So we're going to actually divide by that number so we can convert into moles of calcium phosphate. And so this atomic mass, the molar mass is going to go on the bottom. And as a review, to calculate molar mass, it's going to be the sum of all the atomic masses. So the molar mass of this compound is going to be, we have 3 calciums in the formula. The atomic mass for calcium from the periodic table is 40.08. We also have, we need the atomic mass of phosphorus, which is 30.97, oxygen, which is 16. So we're going to sum up all the atomic masses. So we have 3 calciums, which are 40.08. Our formula has 2 phosphoruses because we have PO4 taken twice, so we have 2 phosphates, each with 1 phosphorus. So we have 2 phosphoruses. The atomic mass of phosphorus is 30.97. And then for oxygens, we have 4 from each phosphate, 2 phosphates for a total of 8 oxygens with an atomic mass of 16 each. And so what we come up with for the molar mass of this compound is 310.18 grams per mole. All right, so that's the number of grams of compound in 1 mole. So if we divide by that number, that'll give us the number of moles that we have in this 5-gram sample. All right, so that gives us moles of compound. And then from here, there's a couple different ways we can go. But what we should recognize is that if we multiply by Avogadro's number now. So we have moles, so the temptation to be like, oh, just not multiply by Avogadro's number, that would give us the number of atoms. But if we multiply by Avogadro's number now, remember that it's going to be 6.022 times 10 to the 23rd of whatever the building block is for that substance, whether it be atoms, molecules, or in this case what we would call formula units for an ionic compound. So if we multiply by Avogadro's number, this would give us 6.022 times 10 to the 23rd formula units, as it's called, for ionic compound. That's basically the ionic analogy of molecules. They're not really made up of molecules, but it's the same story, just one of these formula units per mole of that compound. But again, what we're looking for here is the number of phosphorus atoms. And so what we have to remember is that each of these formula has 2 phosphorus atoms in it. Phosphorus taken twice. So it's going to be 2 phosphorus atoms for every 1 formula unit. So we have to remember this last step here to calculate how many phosphorus atoms we actually have. And this comes out numerically then to 1.94 times 10 to the 22nd phosphorus atoms. As is often the case on Blackboard, we ask you to take the log of these larger numbers instead of typing them in directly. So the log of that number is 22.29. Okay, so any questions on this problem involving mole conversions? It's this last step here that we often forget. If we're looking for the number of atoms in a formula, we have to keep in mind that Avogadro's number just gives us the number of formula units for ionic compound or number of molecules. The number of atoms, we have to also account for the chemical formula and how many are in that formula. Okay? Any questions on this? Just a few more and we'll wrap up for today. All right, this is a fun problem. So I don't know if you've seen one exactly like this before. So it's a good one to go through. So a metal chloride with the formula MCl3 contains 35.62% chlorine by mass. What is the identity of M? Enter the symbol with correct capitalization. So we learned some problems in this chapter about how to take mass percentages and convert them into chemical formulas. Remember, we take the masses of each element, convert it to moles, and then find the smallest ratio to get the empirical formula. We're kind of doing the same thing here, but we actually have to take a step further because we don't know the identity of one of the elements in the formula. We just abbreviate it as M. But here we already know what the ratio of this is 1 M to 3 chlorines. Now actually I want to see how many of you pay attention in class. So the answer to this question is my favorite element. Does anybody know what that is? Maybe I didn't say it this semester, but I usually do at least once. TC, good guess. That's not a real element. So it would be if it was, but it's not a real element. All right. Iridium, IR. Okay, fun fact. All right, but anyway, now I'm going to show you how to get to the answer. I'm not going to just stop there, obviously. I'm going to show you how we get that answer, whether you remember that or not, that useless piece of information. So how we do this is remember that if we're trying to identify unknown substances, and we want to say, we had a lot of different types of problems like this throughout the semester. What is the identity of this substance based on this and this and this information? Usually the way we do that is we find the molar mass of that substance, either the atomic mass if it's an element we're trying to identify, or if it's a compound we're trying to identify, we need to find the molar mass of the whole compound, and then we match it up to whatever the formula is or whatever the atomic symbol is, as we're going to do in this case. So if you want to find the atomic mass of the metal, M, to be able to identify it, the 2 pieces of information we need are the grams of that metal, the mass, and the moles. Because remember that atomic mass or molar mass in more general is the ratio of grams over moles. So if we have both of those pieces of information about this element or about anything, we can figure out what the molar mass of that substance is. So in this problem, what we're going to do is, because we're using mass percents, we're going to assume that we have 100 grams of the compound. That's the convenient thing to do with mass percentages, because then the percentages just become the mass of each element in the compound. So if we have 100 grams of compound, the percentage 35.62 tells us that we have 35.62 grams of chlorine, and the rest of that 100 grams must be then the other element in the formula, which is the metal. So if we're assuming 100 grams, we have 100 minus 35.62, which is 64.38 grams of our metal M. So that's the number we're going to put up here in the numerator, 34.68 grams, 64.38. Getting momentary dyslexia. So 64.38 grams of our metal. That's in the numerator. And then our next step is going to be to calculate the moles, which we don't have directly. So how do we do that? So the way we're going to do that is we know the identity of one of the elements. So if we know that we have 35.62 grams of chlorine, we can figure out how many moles that is. We know from the formula the ratio of the number of moles of metal and chlorine. So in 2 steps, we can calculate how many moles of the metal we have. So if we want to find out how many moles of metal are in 100 grams, we have 35.62 grams of chlorine. This we know the identity of, so we can find its molar mass and divide by it to get the number of moles of that element. So chlorine on the periodic table is 35.45. So that's the atomic mass we're going to use to figure out how many moles of chlorine we have. So that's how many moles we have. And then from the chemical formula, we want moles of chlorine to cancel and figure out how many moles of the metal we have. The formula is MCl3, which tells us that for every 3 moles of chlorine, we have 1 mole of our metal. Okay? So we end up with 0.3349 moles of our metal. That's the number that we're going to put up here then in the denominator of our molar mass calculation. 0.3349. And that number comes out to 192.2 grams per mole. So then our next step is going to be to go to the periodic table and figure out which element has an atomic mass closest to 192.2. And I already let the cat out of the bag, but if we look, the atomic masses increase as we go. So you have 186, 190, 192.2 is atomic number 77, iridium IR, which, as I said, is my favorite on the whole periodic table. So the metal in this case is iridium, and that's how we would identify it by calculating its molar mass, atomic mass. All right, any questions? Yes? Multiply the molar mass of Cl by 3. But you just did that? You didn't... Mathematically, it's the same. I'm trying to think if conceptually it would make sense to do that. So I guess what that does sort of works, because I think essentially what you did was the first number would have been, well, yeah, so mathematically it's clearly the same. The first number would have been the mass of chlorine in 100 grams, and then the denominator would have been the mass of chlorine in 1 mole. So I guess in some sense that would be, yeah, I'm not sure if it quite works out conceptually, but mathematically you're right, it does give you the exact same number. I mean, this is the way that makes more sense to me, but certainly what you did may have been valid, but I'm trying to have a hard time putting my finger on why that exactly is. Yeah, so, but yeah, sometimes, occasionally you will do a problem in a strange way and still get the right answer, so, good on you if you do that. But I think this is the way to think about it a little bit more straightforwardly in terms of moles and mole ratios and things like that. All right, other questions? All right, just I think 3 more we're going to go through today. All right, number 22 deals with net ionic equations. So we're jumping ahead now to all the way to chapter 6. Typically, I think on this, the way the problems are arranged on the final, you might be like, oh my goodness, we didn't do anything with stoichiometry. I believe stoichiometry comes later. We kind of combined to some extent chapter 5 and chapter 6 stoichiometry topics. They're not going to necessarily be separated on this exam, but you will likely see them. In this case, though, we have we're just looking at net ionic equations. So the net ionic equation for the reaction of sodium hydroxide and iron 2 chloride, and we want to know it contains which of the following species. So you'll notice here that we have both chemical symbols given as well as coefficients. We need to make sure that both of those are correct. Does it have, the correct species as well as the correct coefficient associated with that species once we write the net ionic equation? So what we have is sodium hydroxide is our first aqueous solution that we're combining. So that's just going to be NaOH. Sodium plus 1, hydroxide 1 minus, and that's going to be aqueous. Iron 2 chloride. So again, named a formula, just a quick review of that. So in transition metal compounds, the number in parentheses tells us the charge. So it's going to be Fe2 plus. And then we have Cl minus as chlorine. So the correct formula for this would be FeCl2. So for transition metal compounds, we have to tell you the charge in the name because it's not obvious from the periodic table. So it's going to be FeCl2, also aqueous. And then the two products, we don't change for these types of ionic reactions, we don't change the charge of anything. We just swap the cations and the anions with each other. So sodium is going to pair with chloride to make NaCl. And then iron is going to pair with hydroxide, still iron 2 plus, so it's going to make FeOH2. So writing out the reactants and products first, we again just write out the reactants that are given to us in the problem, and then we swap the cations and the anions to get the products that are present. Once we have that, the two things we need to next do to finish this equation are we need to write coefficients in to balance it, and we also need to figure out which of the products are soluble versus insoluble. So for coefficients, we see that we have 2 chlorines over here, so that's going to make us have 2 NaCl's, and then if we have 2 sodiums over there, we put a 2 there, and that should balance everything. So we need a couple of coefficients, but again, for ionic equations are usually pretty small. The next thing to think about is solubility rules to figure out which, if any, of these is going to precipitate. Sodium compounds are always soluble, anything with a group 1 cation, lithium, sodium, potassium, so on. So that's going to remain dissolved aqueous. Iron hydroxide, most hydroxide compounds are insoluble except for when they're paired with group 1 like sodium. So all the transition metal hydroxides in particular are going to be insoluble, so that's going to be our precipitate marked with an S for solid. All right, so that's the total or molecular equation as we call it. And then to get to the net ionic equation, there's sort of two ways we can do this. The longer and more rigorous way is to write out the total ionic equation first, where we're going to separate all of the aqueous compounds into their respective ions and then cross out the spectators. So that's one way to go about it. The other way is to recognize that for precipitation reactions, the net ionic equation just involves the cations and the anions that combine to form the insoluble product. So there's a couple ways to do this. If we go through the total ionic equation, this is not the shortest way, but it certainly works. We're going to take all of the species that are marked as AQ and we're going to separate them into their individual ions. So 2 NaOH, we're going to make 2 Na plus. I'm going to have to write a little bit smaller than normal to make sure I fit all this, plus 2 OH minus. Our other reactant is iron chloride, so that's going to make Fe2 plus. We said that's the charge for iron. And then 2 Cl minuses. On the product side, our NaCl is still aqueous, so it's going to be 2 Na plus and 2 Cl minuses. And then this product here, because it's an insoluble solid precipitate, we don't break it up into ions. It exists as intact FeOH2, and so that one stays the same. So that's our total ionic equation, where we take all the aqueous species and separate them up into their individual ions. We would also do the same thing for strong acids. If we had strong acids in the equation, those also divide up into H plus in anions, so those behave very similarly. And then once we have this, we can cross out the spectators. Those are the ones that appear on both sides of the arrow. So we have 2 Na pluses that cancel out with those 2 Na pluses. We have 2 Cl minuses that cancel out, one on each side of the arrow. And that leaves us then with an ionic equation that's going to have, again, just the ions that are combining to make the insoluble product, FeOH2. Conventionally, we write cations first and then anions, although you don't necessarily have to do it that way. That's not going to be an issue in any of these problems. So we do Fe2 plus 2 OH minus, combining to make our insoluble iron hydroxide FeOH2, iron 2 hydroxide more specifically. All right, so that's our net ionic equation. We want to know which of these following species appear. So NaCl is not in the net ionic equation. That's not an insoluble compound, so it wouldn't appear as a solid. Na plus was a spectator, so we got rid of that. So that's not in our net ionic equation. So what we have is 2 OH minus is present, FeOH2 is present, so the answer would be then 2 of these are appearing in the net ionic equation. Two OH minuses appears in one of our reactants, and then FeOH2 solid is our product for the net ionic equation. All right, any questions on this concept? Okay, on to number 23. Another major topic in chapter 6 now was molarity of solutions. So again, the definition of molarity being important here. So we want to know the molarity of perchlorate in a solution containing 3.58 grams of aluminum perchlorate dissolved in 125 milliliters of solution. So the first thing we again need is the formula of the compound. So we're getting a lot of reviews on compound formulas. So as we saw earlier, the charge for the aluminum cation is Al3+. It's not the most obvious one from the periodic table, but it's located here in group 3. So it's going to lose 3 valence electrons and make a noble gas cation, noble gas configuration cation. So it's going to be 3+. Okay, so aluminum is 3+. Perchlorate is another one of those oxo anions, which is ClO4-. So we especially need to know the charge in this case to get the formula right, which is AlClO4 taken 3 times. So aluminum perchlorate has this formula, which we're going to need as we'll see to solve this problem. And then what we're looking for here is the molarity. So just like when we're calculating number of moles or number of atoms, number of molecules, stuff like that, we have to look closely at which quantity are we actually trying to find the molarity of, which substance are we looking for molarity. We're looking for the molarity of perchlorate individually. So remember, when we dissolve the compound in water, it breaks up into aluminum cations, which is the Al3+, and it breaks up into perchlorate anion, ClO4-. We want to know what is the molarity of just the anion, ClO4-. So what we need then is the molarity of ClO4- is defined as the moles of perchlorate, not the moles of the whole thing, but just that anion divided by the liters of solution. All right, and then looking at what's given in the problem, we're told that we're making 125 milliliters of the solution, so that's our volume. We just have to convert it to liters by dividing by 1,000. So the volume of solution is going to be 0.125 liters. Again, by now we should be pretty quick at doing conversions between milliliters and liters. We just divide by 1,000, move the decimal place over 3, however you want to think about that. And we just need to calculate how many moles are in this solution. So we know, again, it's a very similar calculation to what we did before, where we know the grams of the compound. We have to figure out how many moles of the anion are present in that. All right. So the moles of ClO4-, which is what we need, we're starting with 3.58 grams of aluminum perchlorate that we're dissolving. I left out the gram. The first step is going to be converting to moles by dividing by the molar mass. Molar mass is given to us here, so we don't have to calculate it in a separate step. It's 325.32. So grams cancel. We have moles of aluminum perchlorate, but again, we have to be careful not to just stop here, because this is moles of the whole compound that we dissolved. What we want is the moles of perchlorate once it is dissolved in solution. How many of that? So there's going to be 3 moles of perchlorate for every 1 mole of compound. That's because our formula has 3 perchlorates in it. So 0.0330 moles of ClO4- is what we come up with. All right, so again, the commonly forgotten step is this last one here. So then we're going to take that number. That's not the final answer. We're going to take that number and we're going to divide it. I probably shouldn't put a box around it so people think that's the answer. We're going to take that number and we're going to divide it by the volume of the solution in liters to get molarity. So it's going to be 0.264 molar. I believe this is a numerical question, so you would just enter in that number there exactly in 3 decimal places. All right, I also get questions a lot. Now we're back into the portion of the course where we do a lot of numerical questions, and I've gotten asked this a lot, and I think most of you have already figured out, but just in case you're not clear on it, we typically specify how many decimal places we want, and I recommend if you're doing intermediate calculations, don't round to anything less than that until the very end. If anything, keep an extra decimal place in your intermediate. So like, I kept 3 significant figures here because that's what we wanted our answer in. So make sure you don't do too much rounding in the middle, because that sometimes will cause your answer to be off from what it should be. So only try to round at the end. Obviously you can round a little bit in the middle, but don't round too much. So at least keep, if we want 3 decimal places, keep at least 3 significant digits the whole time, and you should be fine. Okay, questions on this one? All right, I think we're going to finish our last one for today, which is balancing redox equations. All right, so for balancing redox equations, this was, again, a topic that was covered in Chapter 6, and one that we had covered pretty extensively on the second midterm. You'll recall that there was 2 questions on midterm 2 that required us to balance these. So this is bringing us back to that, and there will likely be one on the final that involves this as well. So for balancing redox equations, the first thing we do is we assign the oxidation numbers of all the elements on the reactants and product side. So definitely review those rules if you haven't, since we haven't used them in a while. So for oxidation numbers in covalent compounds, typically hydrogen is +1, oxygen is -2. There are very few exceptions to that. And then we're going to get nitrogen by difference. So the sum of all these has to be equal to 0. So we have 2 -2s, and a +1 is -3, which means we need a +3 on nitrogen to make those add up to 0. So the oxidation number for nitrogen start out with this +3. H plus is an ion by itself, so it's just going to be the charge of that ion, which is +1. So anytime you have ions by themselves, it's just going to be the charge of the ion individually. CR2O72-, which is called the dichromate anion, probably the most complicated of the polyatomic ions that you need to know, but not necessarily for this problem. You don't need to know the name, but the formula is CR2O72-. When you have polyatomic ions, the sum of the oxidation numbers has to equal the overall charge, not 0 in that case, but whatever the overall charge is. And so for CR2O72-, we have, again, 2- on the oxygen, -2 for the oxidation number on oxygen. We have 7 -2s, which is -14. We want the sum to be equal to -2, so that's going to be a total of +12 for chromium, but there are 2 of them, so each is +6. All right, so again, the algebra there was -2 was the overall charge. That's going to be equal to 7 oxygens, which are -2 each for their oxidation number, plus 2 times +6 for chromium. So each chromium is going to end up being +6 to make sure that this relationship is true. The sum of the oxidation numbers equals the overall charge. So that's probably the toughest one we'll do. NO3-, similar story, but not as complicated. We have 3 oxygens is -2 each. -6, we need to have them add to -1, so that's going to be +5 for nitrogen. So nitrate is the most oxidized form of nitrogen. It's a group 5 element, and +5 would be its maximum oxidation number, which is what we have here. The rest of these are pretty easy. Chromium by itself, so it's just the +3 charge that comes with the cation. Water is our old friend of -2 and +1. All right, so those are all the oxidation numbers. The next step then is to find which ones are changing. So nitrogen is going from +3 to +5. And then chromium is going from +6 to +3. So the ones that are changing we tie together, and the number of electrons that are involved in that change is going to be given by the difference in the oxidation number as it changes. So nitrogen goes from +3 to +5. That's a difference of 2 electrons. It's technically losing those 2. And then when we're counting electrons for chromium, we have to be a little bit careful how we do that. So this is Cr2 with 2 +6s. This only has 1 +3. So the way I like to handle this is to remind myself that whatever the coefficient is going to be on chromium, this coefficient has to be 2 times whatever that is to make sure that the number of chromiums is balanced. So if this has 2 chromiums in the formula, we need to have 2 Cr3 pluses on the other side. So when we're counting electrons, each chromium is going from +6 to +3. So that's 3 electrons for each chromium, but there's 2 of them that are doing that because there's 2 in the formula. So in reality, this is going to be a 6 electron process. And what we want is the number of electrons to be the same. So if this is 6 and this is 2, how do we make them the same? We're going to triple this one, multiply it by 3. Now they're both equal to 6 electrons. And the way that we triple it, we put coefficients of 3 in front of both of those on the reactants and product side. Okay? So then writing out what we have so far, we have 3 HNO2 H plus we haven't done yet. This coefficient we're going to set at 1, and we're going to keep that at 2, so we don't want to change those either. So it's going to be CrO7 minus, goes to 3NO3 minus, that was the other coefficient of 3, 2 Cr3 pluses, we keep that, and then water. And then as we said, the last thing we're going to do is balance the water and H plus. So we use water to make sure the number of oxygen atoms is the same on both sides. We're going to do that first, because however many waters we put is going to influence how many H pluses we need. So on the left side of the equation, we have 3 times 2 is 6, plus 7 is 13 oxygens. I'll jot that down. So we have 13 oxygens on the left. On the right, we currently have 3 times 3, which is 9. So we need 4 more, so we need to have 4 waters to provide those 4 extra oxygens. Remember, we don't want to change the coefficients on any of the species that we already balanced up here. Those are going to be fixed. We're only going to change water and H plus. So that gives us 4 waters, and then for H plus we have 8 on the right side, 4 hydrogens. 4 times 2 is 8. 4 waters with 2 each. On the left side we have 3 here, so we need 5 more to make a total of 8 on both sides, so that's going to get a 5. All right. So that's how we balance water and hydrogen. We do it by inspection just to make sure that we have the same numbers of oxygens, same numbers of hydrogens on each side. And then this is asking for the sum of the coefficients. So the sum, we have 3 plus 5. Remember, no coefficient means a coefficient of 1, so don't forget those. And sum of all the coefficients, so that's the reactant side. The product side, we have a 3 and a 2 and a 4, and that adds up to give us 18. All right, so often, again, when we're balancing these, we'll ask you for something about the coefficients, either an individual coefficient, a sum of coefficients on one side, or in this case, the whole thing. All right, so that takes us to the end of what we're going to do today. So in class on Monday, the last day, remember that we have course evaluations at the end, but before that, we're going to cover these last 10 questions, which will basically be the exam 3 material, so all the most recent stuff we'll review in class on Monday. All right, so we're getting into the final stretch next week. It should be an exciting time for all of us, and I look forward to seeing all of you then as you get ready for your final.